It's a great pleasure to have Professor Eugene Zima from uh, Waterloo, Wilfrid Laurier University, will speak about effectively, multi- effectively multiplication and division free residue number systems. As usual, please feel free to interrupt, but otherwise mute yourself. Thank you.
Thank you. It's a great pleasure to be here. And this is first time when I'm talking not about summation and something related to summation. This is a joint work, which is, well, it goes on for many years. You know, I'm coming back to it. It's a little bit entertaining and mostly out of curiosity. It is inspired by the great second volume of Donknus. Particularly by chapter 4 and sections on modular arithmetic and how fast we can multiply. So this book is with me for 47 years, and from time to time I'm coming back, you know, and I see new problems and try to find inspiration here. So I will try to go fast and introduce something that you already know, modular arithmetic briefly, and then discuss different choices of moduli, Mersenne type, Fermat type. Then turns out there is a binary number system which can be used to visualize or to look for patterns in modular computations, which I will also briefly introduce, and then discuss three-term moduli, trinomials, and many small prime modules, and actually application. All those works actually are implemented in GMP, and we experimented with a fast linear algebra-based modular package. Then we'll make some conclusions. And I just also wanted to mention that this chapter 4 of volume 2 of CNUS, about 40 years ago, it was on my second comprehensive exam. I had to show to the committee my fluency in whole content of chapter 4 of volume 2. And it was about 2.5 hour long exam. I was standing by whiteboard and answering questions from the committee. So, well, I borrowed this image from another great book of Joachim von Surgaten and Jürgen Gerhardt. That's a standard modular computation diagram. When you want to compute something, say, over arbitrary precision integers, you can do it directly, or you can convert to residue number system, select several modules. They are shown as prime here. Well, I not necessarily need a prime, and then do several computations, the same computation, but now in each class of residues, modulo pi1, modulo pi2, and so on. And then you have step of reconstructing result, and you restore. If you have enough modules and they are also large enough, then you will be able to reconstruct the exact answer. So this is standard modular trick. And there are several obvious advantages. If bit complexity of direct computation is capital M of n, where n is a bit size of your input, then modular approach reduces it to r times m of n over r. So plus some overhead which is related to reduction and reconstruction. And if this complexity is not linear, for example, when this is quadratic, then you obviously see the gain. You make computation r times faster. Well, additionally, in each of those, during those computation, you control the size. So if input and output are small, but intermediate results are huge, you avoid expressions, well, intermediate expressions well, and that's why it's popular technique. And finally, a computation in every class of residues modulo particular moduli you can do independently, so you can run them in parallel on multi-core processor and whatever. So those are obvious advantages, and this diagram bears a lot of similarities with standard evaluation and interpolation trick, and some textbooks argue that this is actually the same. This is just one of the instances of evaluation and interpolation. If you look at Keith Geddes and George Laban textbook on computer algebras and Garner reconstruction from modular images and Newton interpolation, as a pseudocode is exactly the same, just use different ring homomorphism. And selection of different evaluation points was studied extensively. There is this great survey by Daniel Bernstein on multi-digit multiplication for mathematics, who actually shows that all fast multiplication algorithms such as Karatsuba, Tom, Dual Tom, Tom Cook, FFT, Schoenhage-Strassen, and so on, they're just different ways of selection of evaluation points in evaluation and interpolation case. And selection of different moduli is not that popular and still deserves investigation. And let's take a look what are our natural requirements when we select several moduli. We want them to be relatively prime, first of all, so not necessarily prime numbers, but they need to be relatively prime. It's kind of agreed that this is better. You still can deal with non-relatively prime moduli that share some small common factors, but then technicality of reconstruction is, well, it's a little bit more involved. So you need to do a little bit more work to do the reconstructions. And of course, since those two parts, this is pure overhead, we would like reduction to be fast, and we would like reconstruction from modular images to be fast. And for different reasons, for several reasons, we also need those, we want those moduli to be about the same size. So we need balance in size, and we need some scalability. For example, if we want to apply this trick recursively with set of large modules and set of smaller modules, we want scalability, right? So those are natural requirements, and let's see. Here is a typical, that's from textbook, borrow from textbook, Garner reconstruction. You are given array of residues and array of modules, and you want to recover integer a, which is equal to r sub I modulo m sub I. So most complex arithmetic operations involved in this reconstruction, well, in reduction and reconstruction. In reduction, we need to be able to divide by moduli fast. And in reconstruction, there is a stage here that pre-computes some useful values, modular inverses, and then there are multiplications by moduli, and there are multiplications by these inverses. And keep in mind that we are talking about large moduli, not moduli that fit computer word, for example. So we want those multiplication can be actually involved. So we want them to be fast. And so I will show how we can potentially get rid completely of this step and replace multiplication by addition and shifts everywhere here. Every multiplication, we will try to get rid of it. Okay? And there are many popular standard reconstruction algorithms, some of them iterative. Instead of computing here inverse of product of m0 to m-1 modulo next moduli, they actually compute pairwise inverses. So you compute mi inverse mi in modulo m sub j. So this is my introduction. Now we will try to see how to choose a moduli. That's our freedom, right? That's freedom that we have. We are not given any restriction on our choices. So how we choose moduli, making both conversion to residue number system and reconstruction as efficient as possible. And you don't need to go very far, because first type of moduli is discussed in the art of computer programming, semi-numerical algorithms. Those are Mersenne type of moduli. Those are not exactly Mersenne numbers. Those are not 2 to the n minus 1, but they are Mersenne type. And using this fact that two Mersenne type numbers are relatively prime if and only if exponents are relatively prime, it is straightforward to select, well, enough relatively prime moduli, right? And then division by the modulus of this shape 2 to the n minus 1 can be replaced by shift and addition. It is written here, but it's actually better just to show it on here. Say I'm already in this domain. I have input A and B are my some residues modulo 2 to the n minus 1. I multiplied them. I got the number which is at most 2n bits. I want to reduce it back, to get it back, to reduce it modulo 2 to the n minus 1. You just split it, chop it here, and you add high bits and lower bits, modulo 2 to the n minus 1. You take care of possible forgot the word. When you got extra bit, when you add carry, you get rid of carry. You just, if you have carry during addition, you just add it back to here, and you will get result. You will get a residue of product without any divisions, right? So it is efficient and fast. And to reduce input, potentially very large number, modulo 2 to the n minus 1, you just do the same. You use the same trick. You use this identity. Any 2 to the n can be replaced by 1 in a class of residues modulo 2 to the n minus 1. So you have your input, you chop it into n-bit pieces, and you add them together modulo 2 to the n minus 1. Effectively, this gives a linear time in the input size reduction, which is more efficient than division with remainder, obviously. Okay, is this clear? So, well, that's great. And so let's take a look at all what those Mersenne type moduli can give us. Relative primality, well, is in place if we select moduli using this, properties that exponents need to be relatively prime. Reduction is fast, as we shown. Reconstruction is slightly faster than is based on direct arithmetic, because multiplication by moduli is fast. Multiplication by moduli of this shape, it's one shift and subtraction. So it is linear in the bit lengths of multiplier. But multiplication by inverses is not really fast, because there is no real structure in inverses. We can make them balance in size, those moduli balanced in size. Scalability, well, I have it halfway crossed out because this is not a simple scalability, and we will just go and look at examples shown in Don Knus volume. So first, one of the earliest semi-successful use of Mersenne type moduli is in Shonkage paper from 1966, before they came up with fast Fourier transform-based implementation. Shonkage tried modular approach. So, and you take numbers of this form for different value of k's. So you fixed k, then for fixed k, you can, for example, consider 6 moduli of this shape. They are all Mersenne type, and they are all relatively prime because those exponents are relatively prime with this choice of numbers. And then if you then you can reduce your multiplication. You make 6 multiplication in each of those modular domains, and then you can repeat it recursively. This is pretty involved process. So, but in original Shonkage paper, it was shown that these ideas allow you to reduce n-bit number multiplication to R multiplication to multiplication modulo R different modules of Mersenne type, which are relatively prime, and it will give a recurrence for complex time of multiplication of this shape. And well, that's a comment I have seen before in other paper that says that we shall not dwell because there is better method. And this method based on modular arithmetic. So in this case, you reduce multiplication of n-bit numbers to 6 multiplication of numbers of size of n over 3 bits. So general recurrence is like this, and you actually always lose to Tom Cook method, because Tom Cook reduces multiplication of n-bit numbers to 2 to the n minus 1 multiplications of n over 2-bit numbers. So it's minus 1 here makes solution of this divide and conquer recurrence asymptotically faster than solution of this. But scalability here means that when you work modulo this number, you can recursively use 6 modules that you obtain by replacing q sub k by q sub k minus 1. So you go to smaller numbers and you repeat this recursively. That's why you get divide and conquer recurrence. And so it is kind of scalable, but not in a sense which I actually want. I can stop sharing for a moment and share another one.
I have a quick question. You're talking about fast multiplication?
Yeah, well, this example was about fast multiplication, yes.
Isn't fast Fourier transform the fastest nowadays?
Well, nowadays they claim there is faster one due to Joris van der Hoeven, but it is not practical. So there is n log n
algorithm.
Yeah, okay. Which is not practical. Do you see maple here?
Yes.
So, well, that's what I just try to reproduce. If I take q sub 4, this is my set of moduli. I didn't want to convert them to binary. Oh no, I did want to convert this. This is my inverse. This is inverse of first modulo M1 mod M6. And you might see some pattern here, right? If you want to multiply faster by a binary number, we would like to see some pattern. And but unfortunately, if I take next one, Q sub 5, this is now a set of larger moduli, then again, I have some pattern here, but it is not the same. So that's why scalability is partially crossed in my notes, because it's scalable in a sense that you can always replace computation modulo large moduli by computation module, several computation modulo smaller modules, and it's very easy to compute moduli themselves, but you still need to work with inverses. You need to pre-compute those inverses, and you need to multiply by them, and there is nothing that actually well, gives hope here in terms of how to make it faster. And if I can share back my main here, I just wanted to make one more comment here. I could not, well, there is an old paper, which is those Mersenne type of moduli, especially Mersenne type primes, very popular. There is paper by Aviesri, Frankel, which considers single modulus of Mersenne type, and it needs to be prime to actually make multiplication in this in field modulus is prime fast. Multiplication is replaced by addition, effectively, of indices. So this is very popular, but I always was curious, okay, why Mersenne? Why don't we take Fermat type moduli, right? So looks also very simple.
Sorry to interrupt again. Avier Frankel, a good friend of mine. So
I
is
know.
this paper original, or he used some previous? So the idea
I believe that this is original paper. I can send you PDF. I have it.
Okay, thank you. I email him.
So
he's 94-year-old. So I tell him about to know what you talk. Go ahead.
Yeah. Well, I remember Aviesri when we met on a Wilf 80 conference. He was an invited speaker. So yeah, that's why I was not able to miss this. So if you look at Fermat numbers, right? Well, Fermat type, it's not Fermat because Fermat is 2 to the 2 to the n plus 1, but Fermat type numbers, well, relative primality is actually also quite easy to guarantee because two Fermat type numbers are relatively prime if and only if binary valuation of exponent is different. Binary valuation is number of trailing zeros in binary in the exponent. And when we proved this, well, we found that this was actually, this follows from a more general result, which was in American Mathematical Monthly from 1990. So for any A, N, and M, A greater than 1, GCD of those two Fermat type expression is either trivial. So when valuations are not equal, binary valuation, and A is even, or 2, if valuations are different by A is odd, or something non-trivial. And it's interesting that this fact is not mentioned anywhere else. That's why we actually proved it first. And then one of the referees pointed out that this is known. And if you look at a book devoted to Fermat numbers, 17 lectures on Fermat numbers, which is 11 years older than Math Monthly, they only have partial result for this, the GCD of those two, 2 to the m plus 1 and 2 to the m times n plus 1 is trivial if n is even. So, but again, relative primality is quite easy to establish, right? And then how about reduction? Well, reduction is also easy. and I will just show you again on this diagram. If I'm already working modulo 2 to the n plus 1, so I'm in 2 to the n plus 1, A and B are residues. If I multiply it, I got at most n-bit number. I want to reduce them. Again, I chop it. And instead of adding, I just subtract. I subtract from high bit, low bit, modulo 2 to the n plus 1. So I have division-free reduction here in the class of residues. And if I take large input and I want to reduce it modulo 2 to the n plus 1, it's again, you chop it in n-bit pieces, and then you just alternate signs. So you take L1 with plus, minus L0, plus L2, minus L3, and so on. So this reduction is actually linear. Again, large input can be reduced modulo 2 to the n in number of steps proportional to bit lengths of input. So this is faster than division with remainder. And yeah, again, it is all based on the fact that when I'm in class of residues modulo 2 to the n plus 1, my anything which is 2 to the n is just minus 1. Then 2 to the 2n is 1, 2 to the 3n is minus 1, and so on. So that's easy. Now, there are different strategies to select numbers whose exponents have a different binary valuation. So you want them relatively prime. There is block strategy. If I fix n and take numbers of these shapes, those exponents will have different binary valuation. Or there is shift strategy. I take arbitrary a, and then if my exponents are of these shapes, they all have different binary valuations. So those moduli are pairwise relatively prime. And unlike Mersenne type modulis, well, for Mersenne type modulis, if I want to store a modulus, I need to store an exponent. So my storage complexity, space complexity is log m, where m is my moduli. And if I need to store those, it is actually log m, because I only need to store a and index, nothing else. I don't need to store this number in expanded form. The same here, I just need to store n and I. And I don't need to store anything else. So, and here is the first surprise that we found. First surprise was that if you use shift strategy and you take a product of moduli and look at inverse modulo next modulus in this sequence, then this inverse is very sparse. It has only 3-bit set, right? This inverse is very sparse, and for any value of a, your inverse always has only 3 terms. So multiplication by such inverse is effectively linear time, because I just need 2 shifts, 1 subtraction and 1 addition, right? And if a is equal to 1, then it's even better, because inverse is just power of 2. Well, because in this case, this product of, now we are dealing with Fermat numbers, they are all 2 to the n. The product of first Fermat numbers is next Mersenne number, and next Mersenne, so Mersenne number modulo Fermat number is exactly this shape. So that's great. Well, there is only one little problem here. Like if I use those moduli of this shape in my reconstruction, then every multiplication by inverse is replaced by 2 shifts, addition and subtraction. Any multiplication by moduli is also very simple, 1 shift and 1 addition. So I don't need to pre-compute inverses at all. So we got rid of first block and reconstruction code because those inverses have closed form. I don't even need to store them. I only need to store A and index, right? So this is very good, but they are very disbalanced in size. Balance in size is absent because the next moduli uses number of bit length is larger than product of all previous ones. So which makes them, well, interesting, but not very practical. And that's another comment. This actually works in any base. So if I travel back in time to 1998, 1997, when Maple used for large integers base 10,000 decimal, 10,000 base in a system, then the same works. If I choose moduli of this shape, then and I look at product of moduli and take inverse modulo next one, it is very simple. It is shift, subtraction, addition, and division by 2, which is linear time operation. So, and well, that was shift strategy, and it breaks because of disbalance in size. And there is block strategy. When I choose more or less, well, to remind you what block strategy is, where is block strategy? I hope I can, no, that's Mersenne. Sorry, okay, yeah, here is block strategy. Right. Well, my moduli now more or less balance. The largest moduli may be twice as long as the smallest one. So their size is more balanced. And this highlighted and crossed out, I had, well, because it's so hard to find the pattern when you look at binary. So I didn't see the pattern in inverses for a long time, and I forgot about this. And so to answer the question, are those moduli scalable, and is reconstruction can be made fast enough? Well, I first introduce informally what simple scalability is. So simple scalability is in place if multiplying all exponents by the same number, positive integer number, we preserve relative primality and probably some other interesting properties. So, and in order to talk about this now, I actually need some small tools. This is a small exercise in positional number system. So we introduce a balanced binary numbers, which look very similar to balanced ternary numbers. And I have those here. That's a ternary computer, which uses balanced ternary system. And this is experimental model made in 1958. That's when I was born. And that's Nikolai Petrovich Brusintsov, who was my instructor. And that's computer I used in fourth year. That's serial model. We had 50 pieces made in Kazan city. That's balanced ternary number system used in this computer. So
in 1958, there was a computer in the Soviet Union?
Yeah.
I say it was a capitalistic, cybernetic was capitalistic.
Yeah, well, and actually Nikolai Petrovich Brusintsov, he was my instructor in one of the courses.
I was brave.
and balanced ternary is so beautiful, so I always have it in mind, and I figured out that there is actually maybe some use of it if I just look at binary representation, but I allow coefficients to be -1, 0, and 1. So it is the same as balanced ternary, has very similar nice properties. Most significant digit defines the sign, so you don't need extra bit for sign, or you don't have problem with representation. It is normal form because 0 is uniquely represented also, but it is not unique. If you take 30, you can write it as a binary, which is also balanced binary, right? And you have also alternative representations like this and like this. But turns out, surprisingly, this is fixable in very simple way. So you say that number is sparse balanced binary if it can be written, if you write it in this form, but you have no consecutive bit set. So you cannot have 1 beside 1 or 1 beside -1.
There's
So
another go to the second of representation with Fibonacci numbers. It's also not unique, but you make a convention.
yeah,
So Fibonacci, second of. So it's
yeah,
another go.
yeah. But now with this extra requirement, this is unique. This representation is unique, and also this sparse representation is the sparsest one. So you cannot write the same number with less bits set. So this is sparsest one. And now with this representation in mind, I can try to switch to Maple again just to show you. I actually used it here, but sorry. Let me, yeah, here. So those are my Fermat type numbers, shifted case, right? And those are inverses of product. So product of first moduli, modulo next one, right? And you can introduce any scaling factor here. Sorry, I don't want to wait too long. Those are inverses. You see, the exponents are much larger, but you still have only 3-bit sets. And this is exactly in sparse balanced binary representation, right? Because there are no 2 consecutive bits set. And this is very easy now to find the pattern. And also, I just need to reshare my screen. Sorry, I need to reshare my main screen. So with those balanced numbers, now you can introduce what scalability means, simple scalability. This is operation when every exponent is multiplied by natural number u. Well, you can also treat it as a change of basis. You have sparse binary balanced number, and you change basis from 2 to 2 to the u. So you have the same set of bits, just representing much larger numbers. But what is important when you scale, you preserve relative primality in obvious way, because when you multiply exponent by any number, then valuation in each exponent is increased by the same side, by the same value. So if you had 2 valuations which are not equal, now those will be also not equal. So you can now scale those moduli by any factor. And if you found some interesting moduli with properties that inverse has nice properties, then you can actually scale and use it. And this doesn't work for Mersenne type moduli, because if you scale Mersenne type moduli, you got non-trivial GCD immediately, right? That's what what I mean that scaling for Mersenne type is not simple scaling. It's some artificial scaling which doesn't preserve patterns, for example. And here is this some interesting properties that I mentioned, that computed inverses preserve sparsity under scaling operations. Say I have those my two Fermat numbers which are relatively prime, inverse in sparse binary representation as this one. I scale by factor of 2, I have the same number of bits in inverse. So, well, with this little tool in mind, unfortunately, Maple cannot handle polynomials with unknown degrees properly, so I cannot do it automatically. You still have to work manually to look at something, but for block Fermat numbers, if you start with index greater than 1 here, when you select moduli, you always will have, first of all, sparse inverses, and they are scalable, which means that you can scale by factor million and get a moduli of, inverse of great size that has only 8-bit set. So multiplication by such a moduli is linear time. Well, so to work out those linear properties, you just use some basic facts. I just read them here, don't read them. That's how to divide Fermat number by Mersenne number with remainder, how to divide Mersenne by Mersenne, and so on. But you consider two moduli with the same M and different M and L from block L and M, and you execute manually a mix of steps of binary Euclidean algorithm, binary GCD, and regular GCD, and you continue this way, and you got closed form. For example, for M equal to L plus 1, here is closed form for inverse. And then you repeat the same trick for scaled numbers. So you take the same exponents and scale them. You repeat the same steps of extended Euclidean algorithm, and you got closed form, and you see that number of bits set is the same. So this inverse is scalable, and now I can use it. Or you can use Maple, right, to choose satisfactory group of moduli. In Maple, it looks very simple. You just sorry, I lost my button to share Maple here. So you start Maple. They cannot fix it for a long time. So here are my block of exponents. Here is my scaling factor. Here is my list of moduli. Here is my scaled list of moduli. So this is my list of moduli here. Here is my scaled list of moduli. And I'm in wrong worksheet, sorry. I'm just in wrong worksheet somehow, yeah. Or was it correct? Oh yes, sorry, I was in the wrong worksheet, but it is the same. Trick is the same. So here is my two lists of moduli, and you see that's inverse first moduli, inverse modulo third one, and the same number of bits set when it's scaled. Here is another one, and I like it. Or you can try all. You can try all and see which one you like. So you can just run. And they are all sparse. Don't be scared by this moduli with 63 terms. Because it is 63, if I scale it by factor million, I will have 63 bits in a 100 million bit long number set. So multiplication is still much faster than regular multiplication. So you can play with maple. There is a problem here. Well, there are two problems. One problem that I have only 2 minutes left, so I will try to accelerate. Well, I just make one comment that this can be viewed as evaluation of sparse polynomial with no two consecutive non-zero coefficients, right, at x equal to 2 or scaling at x equal to 2 to the y. The problem is that moduli size grow very fast when you need many moduli, because if you need n moduli, you have to have 2 to the n, right? So moduli grow very fast, and it looks like not practical. So I will probably skip over. I just want to show a practical example when we use this in implementation. So I will skip 3-term moduli when you can also have very fast reduction compared to division for different size of input. And you can have very fast reconstruction because inverses have nice sparse scalable property. And we get to this, there is a library which uses a very fast linear algebra and many, many small primes fitting actually 29-bit primes to do, they use for fast matrix multiplication with large integers entry. And this library deteriorates when input size, when matrices have entries larger than 2 to the 18 bits. And idea is actually to make it work, to implement two-layer modular arithmetic. On first layer, you use large moduli, few large moduli with nice inverses. And then, as you see from this table, for example, it's 8 times faster on the same task for very simple reason. And I just have a minute to complete the reason. And the reason is visual here. That's how a flash FPAC works. It spends time on preprocessing depending on input size, then simultaneous conversion to residual number system based on fast linear algebra, then multiplication of matrices in every RNS, and then reconstruction. And now, when we introduce upper layer, we say selected 4 moduli, large ones. We have 4 problems now of smaller size, and preprocessing is common for all of them. It takes smaller time to preprocess, and this can be reused in every branch. And then your simultaneous conversion also is faster. So everything in blue is saved time. Then your multiplication is faster because you have smaller size, 4 problems of smaller size. Reconstruction, and there is this last reconstruction on upper layer, which is very fast. It's actually, it should be very tiny bar here, because this is extremely fast because it's linear time. It's multiplication-free reconstruction. So, and it works, and yeah, this is just timing that shows that's when inverses are not computed. And this one is Mersenne type. That's time to compute inverses during reconstruction and then reconstruct. So it is always faster with Fermat, with trinomial numbers. And my conclusion is that, well, it seems to be practical and it bears a lot of similarities with sparse polynomials, but unfortunately, I asked many experts and nobody can tell me nothing about, for example, about pattern in polynomial remainder sequences for trinomials. Say, I have trinomial. I know that those two are relatively prime if this condition holds. And if I scale degrees here, all exponents by the same factor, this condition will hold, so they will be relatively prime. Nobody can tell me what is a polynomial what is the structure of polynomial remainder sequence for those. So, well, this is not very hard topic. It just, requires some attention probably, but there is little hope because.
Okay, sorry, Eugene. -3 minutes left, so please.
Okay, I stop here.
Okay, thank you very much for
Thank
very
you.
great talk about multiplication. It's amazing you can still say something interesting and new about multiplication. Any questions? Well, I have a question. So, using this assigned binary, is it original with your advisor, with the one you mentioned?
No,
Who originated
this
assigned binary?
no, balance ternary is well known. Balance binary, I didn't see it. I just did it 2 months ago. I decided to look that this is actually unique. If you require it to be sparse, it will be unique and sparsest. And I don't know. If someone can tell me a reference, I failed to find sparse balance binary number representation. Arithmetic is very simple. So
yeah,
you
because
can,
it's very natural. If you have a balance, you can put it on both sides. You can weigh weight. So a lot of puzzles use it. So it's really.
oh yeah,
really nice.
yeah. Balance ternary is used in all those puzzles and entertaining mathematics a lot. Balance binary is not that useful for weights, but it is useful just to spot the pattern in Maple, because you see that, you have something because you just did inverses of 10,000 bit numbers and you have only 3 bit set, right? And then you start to suspect.
Interesting. Other question to you,
Eugene, I had a question.
Yeah.
Go ahead.
At the very beginning, you mentioned that the moduli that you're using are pretty big. They're larger than a machine word, in fact, at least in some cases. What are some applications where we're using moduli that are so big? You mentioned really big matrix multiplication, but other than that, what are some examples of when we'd be using such huge moduli?
Well, whenever you have huge integer coefficients, you're working with polynomials with large integers.
Okay.
So you can do the same trick, right? So yeah, anything which involves with matrix, it's not only matrix multiplication. Even if you suspect that, or you have advanced knowledge that your matrix is unimodular, right? And you would like to actually to compute determinant. Well, your intermediate expressions are huge, right? But when you use modular, you control everything under size, so you can compute determinant very fast.
Right.
And then check if it is, do some extra, But those modulars those special type moduli, they are large just by construction, right? Because if you want 4 modules, you can feed them in machine word. Oh, no, sorry, not 4, 2. If you want 4, it's already, right?
Very big, right?
It is not enough to have machine word to have relatively prime moduli. So, but yeah, again, this idea with two level, when you introduce layer, to get something to amenable size, right? That's where you need large moduli, right? I have 4 moduli which are large. I reduce size from 2 to the 22 bits to 2 to the 18. Now each one is treatable here much faster, and my reconstruction at the end is very cheap. So that's so far that's the only use where. Second use is just curiosity, entertaining, right? Because it's very funny that like this fact about shift Fermat prime, it was unknown. Like that this is always like this one, that this inverse is. Whoever plays with numbers, right, would appreciate such a fact, right?
Right.
Yeah, interesting. More questions to Eugene? Well, thanks so much.
Thank you so much for your attention, and I hope you have great summer.
Thank you. It was a great talk to conclude this. This concludes this semester, and hope to see you in the fall. It was a great way to conclude it. And
oh yeah, I will come back, definitely.
okay.
I will come back to seminar.
So everybody have a good summer, and thanks for coming.
Thank you.
Bye. Thank you.
Bye. And I will send you slides.
Yeah, please do. Thank you.
Okay.
And the recording will be available soon. We'll let you know. Thank you.
Okay.
And I'm going to send Aviese Frankel the slides. And
Yeah, I will send you his paper. This from 96. It's very interesting, you know. Yeah, you reduce multiplication to addition of indices.
Yeah,
And
okay. Thank you. Goodbye.